The objective today is to better understand RFC 8391, aka Extended Merkle Signature Scheme. So this RFC actually has quite a few contributors here. And if you don't know what I'm doing with these videos, basically I'll provide a summary to the best of my ability of these RFCs I'm reading. And what I do beforehand is just kind of mark them up, as you can tell here. And just to keep you engaged, I'll ask you, but also I'll be asking myself questions that I need to be able to answer. Why? Because I love learning. So this RFC starts with an abstract that says, this note describes the extended Merkle signature scheme. It's a hash-based digital signature system that is based on existing descriptions in scientific literature. This note specifies Winternitz's one-time signature plus a one-time signature scheme, XMSS, a single tree scheme, XMSS to the MT, a multi-tree variant of XMSS. Oh, so there's a question for us. What is XMSS to the MT? And the answer is, it is a multi-tree variant of XMSS. Now, both of these XMSSs, they use WOTS+, which, Winternitz is just a cool name. So this Winternitz one-time signature plus as a main building block, so that's why I put a square there inside of a house, unless we're talking about XMSS to the MT, in which case the building block is still there. Anyways, what XMSS provides is a cryptographic digital signature without relying on the conjectured hardness of mathematical problems. Instead, it is proven that it only relies on the properties of cryptographic hash functions. XMSS provides strong security guarantees and is even secure when the collision resistance of the underlying hash function is broken. It is suitable for compact implementations, it is relatively simple to implement, and naturally resists side channel attacks. So I drew a little picture right here of this stop sign being XMSS. It's a stop sign that is stopping what? Side channel attacks. So there's question 2 for you right there. Now, unlike most other signature systems, hash-based signatures can so far withstand known attacks using quantum computers. So I'm like, what? That is really cool. And the reason you're seeing this RFC number 8391 pop up after I've been doing some simpler, more basic RFCs is because I did not know whether I should start from the beginning and read these for my own edification. I had to look up that word just to make sure I used it correctly. Yeah, I didn't know whether to start at the beginning or the end, as in the latest, greatest RFCs, so I decided to actually do a little bit of both. So this one actually came out in May 2018, so we're talking cutting edge technology that I am trying to digest here. So I read the abstract to you here. Let's go ahead and just start going through my big takeaways from the paragraphs, and very likely, since this RFC is particularly long, I'll go ahead and break it up into a couple parts. So in this paragraph, they talk about how the document is just an Internet Research Task Force document. You know, we love our acronyms in tech, so IRTF. And then later on, they talk about the Crypto Forum Research Group. I had never heard of these guys. I'm inclined to ask the questions, are these the guys I'm arguing with on Stack Exchange? Well, actually discussing. I'm not much for arguments. But it's saying that this RFC represents a consensus of this group of the Internet Research Task Force. Then it goes on to say that documents approved for publication by the IRSG. Now I'm wondering what IRSG is. I'm looking around. Did I miss something here? Is this a simple typo? Well, anyways, it says that documents approved for publication by the IRSG are not candidates for any level of Internet standard. And to back up this statement, I guess it says see section 2 of RFC 7841, so maybe that'll be a to-do for me. But let's just move on to the good stuff. Like I was saying in the opening here, and like you could see in the title, XMSS is an extended Merkle signature scheme. It is a thing that can beat quantum computers in the areas of security, so I am very interested. We can go through the table of contents. This note on post-quantum cryptography sounds fun. And as I scroll through, there's a lot of basic things. And if I'm understanding this right, it sounds like WOTS plus, which is that Winternitz is a one-time signature plus. It sounds like this is a public key exchange thing. Then I made the font really small because, yeah, there's a lot to get to in the paper, and it looks like it ends after 74 pages. So a 74-page RFC is a pretty big RFC. I mean, compare that to the 7871 on subnets that I'm about to read. That one is only 30 pages. So in the introduction, it says a cryptographic digital signature scheme provides asymmetric message authentication. Asymmetric is the good kind. It's the public key kind. So a little smiley face there. The paragraph goes on to say that one-time signatures are good for one message only, but if it's a many-time signature, it'll need to be its own little system because using a one-time signature on multiple messages would be a bad thing, or at least an insecure thing to do. So I found it interesting that this signature is named after a man from 1979, Merkle. Crazy to think that something that can stand the test of quantum computers started in 1979, or at least we're pivoting from what that Merkle guy had started. I do not know what BDH11 means, and I tried to do a little research and didn't get very far. I think it might just be another version of this. But my question mark right there will remind me to research further and at a later time. And we're still in the introduction here, so the RFC goes on to talk about some other people and some other work that has been done. The paragraph ends by saying a reasonable next step toward introducing hash-based signatures is to complete the specifications of the basic algorithms LMS, XMSS, and Sphinx. So that's a good question. What algorithms still need to be finished? Your answer, the LMS, XMSS, and Sphinx. And it seems like in the cryptography world, a lot of these acronyms are just related to people's names. So this is the Leighton-Macaulay specification, I believe, or signature or scheme. Whatever it is, you tell me in the comments or in class. So this paragraph says that XMSS is the latest stateful hash-based signature scheme. It goes on to say that multi-tree is a solution to a slowness. It says that in particular it is not required that the cryptographic hash function is a collision resistant, which I said is so weird. Maybe does that mean SHA-1 is a good enough hash to use within XMSS to get the security you're looking for? As I'm reading through the paper, I like to continuously try to break apart these acronyms so I remember what they stand for. Therefore, OTS is, yes, a one-time signature. This paragraph really did just seem to give us like another table of contents, but in a paragraph form. If I'm remembering correctly, IANA is the bigger registry body, and ARIN is just one example of what the IANA is overseeing. So Internet Registry, as in you go to these guys to get the IP address for the brand new ISP you're starting. Extra credit if you want to start your own ISP. Now right here I'm just saying this seems like such a weird paragraph to me, but of course bring on the experiments. I'm ready for some analysis of algorithms, but unlike a lot of RFCs I've read, and maybe that's what makes this one so different to me is because this is one that's so new. What I'm trying to say here is unlike other RFCs I've read, this sounds so like unsure of itself. But RFC stands for requests for comments, so I guess right now I'm adding my comments to it. But let me go ahead and just read the paragraph so you kind of get a sense of what I'm saying here. They said that many of these algorithms come with specific restrictions. For example, change the classical interface or less cryptanalysis of proposed parameters in established schemes. CFRG has consensus that all documents describing post-quantum technologies include the above. I just have to highlight this. It's such a cool sounding word. Post-quantum technology documents must include the above paragraph and a clear additional warning about any specific restrictions, especially as those might affect use or deployment of the specific scheme. The guidance may be changed over time via document updates. So I go to the paragraph above, like it says all post-quantum algorithms documented by the Crypto Forum Research Group are today considered ready for experimentation. So I just don't understand what they're trying to say here, that all documents describing post-quantum technology include the above paragraph. Unless they're saying that the warning that they're required to give in terms of like we're just experimenting, like this paragraph serves as that warning. So since we're reading a RFC about post-quantum cryptography, just everybody realize that this is a warning. I am just experimenting, or these guys are just experimenting with these algorithms. And in a little bit here, we're going to get to see some of those algorithms, which looks pretty cool. But also when reading paragraphs about code is kind of rough, so you're going to see that in a second. Let me get there though. In contrast to traditional signature schemes, the signature schemes described in this document are stateful. That's important to remember, meaning the secret key changes over time. They go on to say that developers should not use the schemes described here except in systems that prevent the reuse of secret key states. So I wonder how common are systems that prevent reusing particular keys. I'm going to start doing little red X's once in a while when I think I found typos. There's a few of them. You're also going to see me talking to myself here because they have pretty strict guidance on what all capitals mean. It's not like the paper is yelling at you, but they have a very specific meaning, as in their thing will not work unless you exactly must do something or must not do something. It gets confusing. I'll take this sentence as the example. The API must be able to handle a secret key state, and in particular this means that the API must allow to return an updated secret key state. I think they meant to say that the API must return an updated secret key state. So for XMSS to use with WTOS+, your code is required to absolutely have a key state. Therefore, I assume, so we could verify that it was a one-time secret message or one-time signature. I love saying hexadecimal and stuff. I found it funny that they went ahead and explained quite a bit what the hexadecimal format is. So that part I knew. What I didn't know is this whole byte strings thing. They're emphasizing a byte string is just simply an array, so don't freak out over that. I find it strange that they chose to use a big Indian representation, seeing how Intel and a lot of ARM processors are little Indian. But maybe for simplicity's sake they used big Indian. And for anybody watching, primarily my students, if you don't know what big Indian means, if I'm looking at a hexadecimal byte string like this, big Indian just means that this byte is here and then that byte is there, and it's just a real sequential ordering of bytes. Now again, Intel and ARM, they usually, well, unless we're talking Intel always uses little Indian. So what that means is if you're looking at this, it's actually flipped, and the CA is here, then the FE is here, and so on. So if you ever do a hex dump on a program, you might have to flip it, either tell the program to flip it. Maybe because we're talking about bytes, I imagine just flicking bytes away that you're not using. But you could tell the program to flip it so that you could better understand what you're looking at. Reading backwards may be a fun challenge, but definitely not worth the time. So as I'm reading and they're clarifying stuff, they say that the ceiling is, at least in code, it's going to be abbreviated CEIL, and I find this some weird stuff. So I'd imagine if you have a function called ceiling and you put a number in it, or a range of numbers, maybe a byte string, if you put it in this function, it's going to return the smallest integer. Alright, so there's a good question. What will the ceiling function return? And then I'll follow that up with the floor function. So floor is going to return the largest integer. And if anybody is unfamiliar with logarithms, right there is a great quick example. So right here, if I do LG and the number 8, what I'm going to get back is the number 3, because 2 to the third is 8. I always like to tell my programming students not to freak out that programming doesn't involve a lot of math. You just need to be able to add, really. But if you're going to get this deep into computer science, you need to know your logarithms. So we're already up to page 7, and they're just talking about the format of the operators. Instead of an X, a star is multiplication. So I'm just okay, check mark, I got that. I feel like this is strangely worded, but sure, / means you're going to divide. Over here, you're doing some shifting of bits, so that reminds me of that C++ type syntax that I had learned. Right here, they're just reiterating what a byte string is. It's an array. Then they're talking about logic gates. Down here, I just had to reread a few times to make sure I'm really getting it. And here's my example. So if I need to left shift or right shift something, it could look something like this. I have the variable x is 7, and the way that looks in binary is 1, 1, 1. Now if I do x equals a left shift of 1, I take these numbers and I shift them all over to the left by 1, and I add a 0 right there, and that would give me the number 14. But a shift is not just going to always double the number before it. So let's say I did x and shift by 3. I know I skipped one here, but I'm just trying to show you that if I was to move those bits by 3 places, I would get a larger number, 112. I'm not just doubling or something, because to double would be like 14 is 28, and 28 plus 28 is a number that is not 112. So the shifting of bits is kind of funky to see. So then they hit us with these like double pipes, but unlike, in JavaScript, it is not an OR gate. It's representing the concatenation of two variables. So I wonder if I can say this like in cryptography. What does that mean? Alright, so this next part gets kind of complicated. I wanted to give myself more room. It is a little confusing, so I try to write it out. Basically, if I'm understanding this right, that for something to go through an int to byte conversion, what you do is you write byte with 2 parameters, one parameter being the value you want to go through this whole conversion, and the second parameter is the string that it will become, or byte string, so basically an array. I should have probably wrote that up there. So you're going to turn something into an array. So let's say I write byte for y. 4 in binary looks like this. 1, 0, 0. And I just put a padding bit right there for who knows why. Maybe that's something that is explained over here, or maybe right here when it's talking about 32 byte. I mean, whatever it is, whatever the value of a byte string is, once I use this command, then I have y as a variable. It's an array data type. So then if I was to do y to the 0, it would give me 0. If I did y to the first index in the array, then it would give me 1. I am not sure if that's exactly how that works or even close, so I put a big question mark there. As I read on, I was interested to see that they are using a bit mask. It kind of sounds like a subnet mask in networking. And they're using the bit mask against a key, so that really sounds like something in networking. We have these routing algorithms routers use to figure out how to send packets to the right place. But since we're talking cryptography, here they're talking about having a key seed, and then ADRS will be short for address. This paragraph is really just a narration of math, so it's kind of hard to understand when you do that. I'd rather just see, I guess, the equation or the code. The iffy part of this paragraph is when they're talking about compression, because typically compression is like an anti-cryptography thing. I mean, the way you compress data is you look for patterns, and in cryptography, if you were to encrypt something, you're trying to not create any evidence of a pattern, because through like frequency analysis or however the bad guys are trying to break your encryption, they could do so by finding these patterns. But then again, I don't know, maybe first you compress it and then you encrypt it and then you decrypt it and then you decompress it. I just want to take note of that for some reason the paper addresses compression. Now here is where we start getting into multi-tree hash-based signatures. This whole concept of a layer address, it basically sounds like it's talking about the height of the data. And then when they say whenever the type word of an address is changed, all the following words should be initialized with 0 to prevent non-zero values in unused padding words. Moving on, there's a thing called Qian Mask. I love camel case, better than snake case that is. And so here's your example of layer tree type, one-time signature, then you have a chain thing go on, a hash thing go on, and it ends with a Qian Mask. All 32 bits except for that tree address. And even right here, the type being 0, that is distinctly different from down here when that type would be a 1. So let's go back up here. This is basically our multi-tree paragraph. Interestingly, they say the next word encodes the chain address followed by a word that encodes the address of the hash function call. Alright, so this is just such an organizational thing right here. This paragraph is about the L tree case. So, totally over my head, but if anybody's watching this just trying to get a feel for this particular RFC, here you go.